Let's continue with the types of problems we were doing in our last session. So see if you can come up with some reasonable arrows for this reaction.
Okay. Okay. You just draw it on my screen, you mean?
Sure.
Okay. Okay. So that one I believe would be a null reaction because the Grignard would work as either a strong base or a nucleophile, but there is not a good well, there is not an acid, and also there's not a good electrophile there. So we could add an acid, or I mean add a base to make the epoxide more a better nucleophile.
Okay, so let's stop and talk about that for a while. So let's see. So you said there would be no reaction in this case, and what did you say you could do to get a reaction?
Add a base.
And how would that help?
Oh no, sorry, I said that wrong. We actually want to add an acid because we already have a good nucleophile. So we would like to add an acid to make the epoxide more of an electrophile.
Okay, yes, that's right. So the first way you phrased it was incorrect, and now we're phrasing it correctly. At first you were trying to make, you said you were making the epoxide into a better nucleophile, but
Right.
then when you corrected yourself, you explained what the problem with that is. We already have a pretty good nucleophile. We already have a pretty good nucleophile. The problem is that you might be lacking an electrophile. Now, let's see here. Go ahead and number all the carbons so it's easier to talk about them.
Okay.
So why can't we just use carbon 4 as an electrophile the way it is right now?
The oxygen trying to remember the rule on it. It seems like a neutral oxygen does not make a good leaving group, but I may be confusing that.
Okay, yes. So what you said was correct. The only problem is that we have to increase our confidence about that.
Okay.
So what you said was correct, but that's actually a pretty important idea that we have to have a high level of confidence about. Again, to use my favorite analogy, if you ask someone how a bishop moves and they say, well, I think it moves diagonally, that doesn't really mean they can play a good game of chess. You got to be confident that you can move that way or you're not going to be able to plan out the moves. But anyway, what you said was correct. We just had to be more confident about it. Neutral oxygens are not acceptable leaving groups.
Okay.
Neutral oxygens are normally not acceptable leaving groups. Why would we expect carbon 4 to be electrophilic?
It has a delta positive charge because of the oxygen that's attached to it.
That's right. But you usually also need to have an acceptable leaving group. Okay. So anyway, your first analysis here, you had a little trouble putting it into the words, but you were right that it seems like there should be no reaction. Now, however, what we said, so are neutral oxygens acceptable leaving groups?
No, they're not.
No. Well, sadly in OChem, as we've seen, there's always exceptions to everything. Actually, neutral oxygens are usually not acceptable leaving groups, but there are a number of important exceptions. Now, I don't know if you remember studying this in the first semester, but some rings are happier and more stable than others. Some rings have a lot of ring strain because the angles in the ring are not the same angles that the atoms would normally want. And other rings have very low strain. So in particular, the happiest rings are 5- and 6-membered rings. Nature really likes forming 5- and 6-membered rings. Nature really likes forming 5- and 6-membered rings. That's a new idea we haven't talked about that would be good to have in your notes. Any ring besides a 5- or 6-membered ring has some strain. Any ring besides a 5- or 6-membered ring has some strain. In particular, 3-membered rings have the most strain. 3-membered rings have the most strain.
Okay.
Because the angles in the ring are very different from what a tetrahedral carbon would normally want to have. That means epoxides have very high strain.
I see.
Now, obviously that doesn't mean it's impossible to make epoxides, because you can see one right there on your screen. So it doesn't mean it's impossible to make them, but it does mean it's more difficult than to make a 5 or 6 membered ring. So would this epoxide be stable or unstable?
Unstable.
Would that make it reactive or unreactive?
Reactive.
That's right. So this turns out to be one of those pesky exceptions. It turns out that you can use a neutral oxygen in some situations as the leaving group with an epoxide. You can use a neutral oxygen as the leaving group with an epoxide because the ring is so anxious to open. Now, that's not something I would have expected you to remember, so your first answer was correct given what we talked about so far. Given what we had talked about before, your answer was correct. We would expect no reaction, so you analyzed that well, but now we're learning a new idea. So the new idea is that epoxides have very high strain, so they can have a neutral oxygen as a leaving group, which is an exception.
Okay.
And actually, as you go through the second semester, you'll see 2 or 3 other exceptions. There's 2 or 3 other important situations where neutral oxygens can act as leaving groups. So we need to know both the rule and the exceptions. The rule is that neutral oxygens are generally not good leaving groups, but as you go along, you'll learn a few exceptions. Okay, so with that in mind, let's try again to draw some electron-pushing arrows.
All right. Oh. Okay.
So what role did the oxygen play?
Leaving group.
Now, are neutral oxygens usually acceptable leaving groups?
They're not usually.
So why was it possible in this case?
Epoxides, because of the ring strain, are an exception to that general rule.
And you can see now the ring has opened, so the strain has disappeared.
Yeah.
Now the strain has disappeared, so you can see that would be a driving force in this reaction. Okay, so so far so good. So are there any more things that can happen now, or are we done?
I think we're done, unless we add something else.
Like what? So the molecule here has a charge. We're usually not done when the main molecule has a charge. So why are you saying that this molecule is done?
Oh, okay. Perhaps we could have a chain reaction.
Okay, actually that is a fair point. All right, hold up. I didn't actually want to do that. So you saw something I wasn't thinking of. So that's an excellent point. You might have a kind of a chain reaction in this case. I don't think that actually happens because I think all the Grignards get to the epoxides before the O- can get to the epoxides.
Okay.
So that was good thinking, though. I wasn't thinking of that. That was a logical thing to think of. But I think that the Grignards are going to get to the epoxides before that chain reaction. All the epoxides for the chain reaction can happen. Okay. So now remember, we're trying to set this up as if we were setting up a synthesis. Generally speaking, when we're doing syntheses, we want to create neutral products. We want to create neutral products. And if the product doesn't become neutral on its own, which it usually does, we need to adjust the conditions so it can become neutral. So what could we add now in a second numbered step in order to get rid of the charge on this compound?
I believe you could add an acid. That would, because it looks like that negatively charged oxygen would work well as either a strong base or a nucleophile. So if you added an acid, then it would react well with that to lose its negative charge.
Good. So supposing, it looks like what we wanted to accomplish here was the nucleophile-electrophile reaction. So we probably don't want this to act like a nucleophile again, we just want to get rid of its charge. So let's write down what you might be thinking of as adding to get rid of that charge.
Okay, if we added Probably just H3O plus. Then that oxygen could lose its negative charge and become an alcohol. Like that.
Okay, very good. Excellent. That's exactly right. That's exactly right. So we would add the H3O plus then in the second step.
Yeah.
So let's zoom out so we can see the whole thing at one time. Now, what was the solvent when we added the H3O plus?
Water.
We've talked about that. Well, if all you want is for that to do the protonation, why not just put the water in the first step? Why do we have to add until the second step? Why can't we just do the original reaction in water and then use the water for the protonation?
Because the Grignard would act as an acid before it would act as a nucleophile. I mean, not as an acid. I mean, it would act as a base if there is an acid present before it acted as a nucleophile.
Good. Yes. So what would go wrong then?
You'd waste your Grignard and you would not have a reaction on the epoxide.
Right. What exactly would the Grignard do?
It would act as a base and steal a proton from the water.
Right, and that would be even more likely to happen if you would put H3O plus in the first step.
Exactly.
But even if we just put water in, that would be enough to destroy the Grignard, because the Grignard is a strong base. So we haven't quite written this out correctly because we should be numbering the steps to show that they're in separate steps. That's kind of my fault because I didn't quite write it out best to start with. So let's go to my screen and I'll show you how this might be written. Okay. So this might be written like this. One good way to write it would be like this, and another equally good way to write it would be like this.
Okay.
So do you agree that these are two ways of saying the same thing?
Yeah.
Because adding an epoxide to a Grignard is identical to adding a Grignard to an epoxide. The key thing is that that has to happen before the second step. Okay, now one thing that you did that was quite good there is you picked the exact right acid. Now, presumably many different acids could be used in step 2, but there's almost always one particular acid that is used with Grignards, and that's H3O+. We've talked about that in the past. So we may as well stick to the conventional acid. Grignards are almost always used in these two-step reactions. We've talked about that before. Grignards are almost always used in these two-step reactions. First, you add the electrophile. Then you add the protonator. So the point is you can't add the protonating solvent at the same time as the electrophile like we normally would do for these types of reactions. Okay, good. So we learned a couple of important things there. So in an epoxide, is the oxygen an acceptable leaving group?
Yeah, it is.
Even though it's neutral because of the ring string.
Yeah.
So we did have a little uncertainty about that, so let's review. How can you identify a good leaving group? What's the best sign of an acceptable leaving group?
Positive charge.
Positive formal charge. Good.
Yeah.
Are there any elements that can be acceptable leaving groups even with neutral formal charges?
Epoxide.
Yeah, that's right. That's a new one that we hadn't learned before.
Yeah. Yeah, the halogens, chlorine, bromine, and iodine can all be good leaving groups when they are neutral.
So these are ones, whoops, neutral. These are the ones we talked about before.
Yeah. We also talked about H2SO4, how that, you can actually, I guess it would act as an acid. I don't know that you would call that oxygen on the H2SO4 a leaving group.
Yeah, so that's an interesting question. But yeah, we would be H2SO4. We're more likely to think you could kind of use you could kind of think of this as an electrophile and this a leaving group. But that actually is probably not the best way to think about it. It's best to think of this as an acid.
Okay.
And this as an acidic proton.
Got it. Okay.
But in any case, we've seen that the reason this is a strong acid, well, maybe we'll come back to that some other time.
Okay.
Not to confuse things here. Okay. So are neutral oxygens generally acceptable leaving groups?
Generally, they are not.
Right. So I guess oxygen is in some ways the most important element in organic chemistry. Obviously, the most common elements are carbon and hydrogen, but they're usually pretty boring. So usually if you don't have a carbon or a hydrogen, you're oftentimes talking about oxygen. So oxygen is one of the most important elements in organic chemistry, and it's very important to know its reactivity. So neutral oxygens are generally not acceptable leaving groups. That's very important to have memorized, although we also have to have memorized that there are some exceptions. And you learn more exceptions besides epoxides as you go through the second semester. Okay. Let's try to predict the arrows here.
Okay. Now, I'm not sure, but I'm going to guess that because oxygen on the water would be... I guess I'm not sure. It seems like the Grignard would be more reactive because it is a stronger base, or it has basically the equivalent of a negative charge on that carbon 3. But H2O seems like it's not very strong. I'm not sure that it would cause a reaction with an epoxide.
Okay, that's a good start for your analysis. Those are good thoughts. So let's try to clarify that, but that's a good start. So is water a nucleophile? Is water a nucleophile?
Water is not a nucleophile. It can be a weak base.
Okay. Well, if water is not a nucleophile, then I'm not sure why you were uncertain. If it's not a nucleophile at all, then there's no question that there just can't be a reaction, right?
True.
So is water a nucleophile?
Well, okay. It does have a lone pair of electrons, so it could be a nucleophile. But
okay. Now let's try to clarify that some more. So what I want us to do is to use some of the concepts from the last session. Do you remember in our last session we said that there were two categories of nucleophiles? There were the good nucleophiles and there were the poor nucleophiles.
Yeah.
So would water fall into the good nucleophile category or the poor nucleophile category?
The poor nucleophile.
How do you tell? What types? Who's in the poor nucleophile category?
Those that have a negative charge.
The question was who's in the poor nucleophile category?
Oh, sorry. The neutral oxygens.
Good. Not just neutral, but neutral oxygens. That's right. Okay. So is water a nucleophile?
A poor nucleophile.
That's right. Okay, that's pretty much what you were kind of getting at before. When you were first describing this, you were on the right track. You just hadn't quite put it in the terms we talked about last time. You were saying, gee, the water is not as good a nucleophile as the Grignard, and that's true. But we can sharpen that by simply saying it's in the poor nucleophile category. Would a Grignard be a good nucleophile or a poor nucleophile?
Good nucleophile.
Just because it's not a neutral oxygen. Now, even things that are kind of in the good nucleophile category don't necessarily do all possible reactions, but they're generally better nucleophiles. Okay.
Okay, yeah.
So, all right, so the water is a poor nucleophile. So your first line of reasoning was basically correct. The water is not a good enough nucleophile to attack this epoxide. The water is not a good enough, even with the ring strain. The one thing we mentioned last time is water really, neutral oxygens can't attack anything that doesn't have a positive charge. Neutral oxygens can't attack anything that doesn't have a positive charge. And even with a positive charge, that's sometimes not good enough. Water can't attack anything that doesn't have a positive charge. Okay. All right, and sometimes even then, it's a little bit difficult. Okay, so the key thing is to use that idea of good and poor nucleophiles we talked about previously. All right, but your instincts here were correct. So this would be no reaction. So let's try to be chemists here and ask how could we adjust the conditions here in order to get a reaction?
Well, if we want something to be a better nucleophile, then we could add a base.
Good. So that's a very logical approach. That is a very logical approach. And you know, in a way, that would kind of work. In fact, yeah. So let's actually look at that. So any particular base you were thinking of?
I was thinking of sodium hydride.
Yeah, that would be fine. That would be fine. That would probably work. In this case, there's actually another base that's more logical. Let's add sodium hydroxide.
Okay. Okay, so we'd want... Okay, we could do H2O. And that base...
So what role do you think the sodium hydroxide is going to play?
Actually, I'm kind of curious. I mean, we put it in as a base, but I almost wonder if it wouldn't act straight as a nucleophile with the epoxide first.
That's a very good analysis, yes. So things that can act like bases can usually also play what other role?
Looks like it would just create the same molecule even if it did interact with the water first.
That's an excellent point as well. Yes, that's a very good point. So to clarify that, things that can act as bases usually can play what other role?
Bases can also act as nucleophiles.
We've talked about how that's one of the frustrating things in OChem, figuring out whether something would be a base or a nucleophile. In fact, do you remember we've specifically talked about O- a little bit? What role did we say O- generally plays in reactions? What role did we say O- generally plays in reactions?
Either a strong base or a nucleophile.
So the key word you said there was either. We said it could go either way, and you kind of have to figure it out based on the details of each reaction. We said it was tricky. We haven't really talked about O- very much. All right, well, I think you've actually kind of analyzed this whole thing correctly in your head already. So you were just saying it would be kind of pointless for the hydroxide to act like a base. Let's actually diagram that out. Show what would happen if it acted like a base.
Okay, if the sodium hydroxide acted as a base, we would have that going on, which would protonate the hydroxide, neutralize it, create what we began with.
That's right. So that's why it's pointless, because we started with water and hydroxide, and we would just get water and hydroxide.
Yeah.
So, in fact, that does happen. That is one of the things that would really happen in your test tube. The hydroxide will deprotonate the water. In fact, that'll happen billions of times. But remember, we're not just trying to draw everything that happens in the beaker. We want to draw interesting things that happen. Obviously, it's not interesting when the hydroxide attacks the water, because that just produces the same things you started with, hydroxide and water. So even though that really would happen in the beaker, it's pointless to draw that. So instead, we might as well just from the start use the hydroxide. So if it's pointless to use the hydroxide as a base, what role should we use it in?
Nucleophile.
Nucleophile. Now what you did is you showed it first acting like a base, and now you're using it as a nucleophile. So that's fine. Let's go back and now just draw this the way we'd really draw it in our OChem class. So you can erase your first set of arrows, or you can redraw the whole thing again if you want. Well, let's just put this in your notes the way so to show what really happens. You might erase what you've already done.
Okay, that sounds good.
On the right, and now let's just show. So let's redraw the water on the left, and now let's just show the hydroxide acting like a base. Good.
Yeah. Then I think you would, now that water would come in handy.
Good point, yes.
Okay.
Okay, excellent, good. Okay, so so your analysis here was a good one. You were seeing the key issues from the start, that it was pointless to use the hydroxide as a base. You can just use it as a nucleophile. This is a little counterintuitive because at first we were saying, gee, we need to add a base to make a better nucleophile. But actually, if you add this base, it's already a nucleophile.
Sure.
And okay. So anyway, this is the most efficient way to do this reaction. Basically, all we're saying is, remember, is the water a good or a poor nucleophile?
Poor.
So the way we can make it a better nucleophile is to deprotonate it, right?
Yeah.
But rather than deprotonating it, why not just add the deprotonated form? That's what we did here. The
Sure.
hydroxide just is deprotonated water. So instead of adding something that would deprotonate the water, like sodium hydride, we just added deprotonated water in the first place. Okay. So that worked out fine here. What role was what role did the O- play in the first step?
A nucleophile.
And why is that reasonable?
Because it has a negative charge on it.
Good. And then what role did the oxygen in the epoxide play?
Leaving group because of the ring strain.
That's right. It's reasonable because of the ring strain, even though it's a neutral oxygen. So remember, in the past, I've been warning you that O- is tricky. It can be tough to figure out whether it's going to act like a nucleophile or a base. And I've been kind of postponing it. But here we've seen one example. So if it's pointless for the O- to play the role of a base, then you might as well use it as a nucleophile. So that's kind of a new rule here. Sometimes it's pointless to use the O- as a base because that would just give you the same products that you started with. So then you could use it as a nucleophile. And by the way, it goes the other way as well. It might be hard to visualize this, but there are some cases where it's pointless to use an O- as a nucleophile because it turns out just to give you the same product that you started with. Because if the leaving group is an O- and the nucleophile is an O-, that might just give you the same thing you started with. So again, sometimes it's pointless to use the O- as a nucleophile, and in those cases you would use it as a base. So I won't give you a specific example of that right now, but now we're starting to see how you can start to tell whether something should act like whether the O- should be a nucleophile or a base. Sometimes one path is pointless because it just gives you the same products that you started with. Okay, did this reaction, so the way we've written this out now, did this reaction occur under acidic or basic conditions?
Basic conditions.
Yeah, even though the hydroxide didn't act like a base, it's still considered basic conditions. We talked about that before. Even if something, so if you have a strong base in the starting materials, that's considered basic conditions, even if they act like a nucleophile rather than a base. So how can we make sure we got this mechanism correct? What should everybody's charge be under basic conditions?
Either positive or neutral. I'm sorry, I was thinking negative, positive, negative or neutral.
So did we satisfy that?
Yeah, I think I was looking at the positive on sodium.
Which we ignore because that's the spectator. Okay.
Yeah.
Okay, so it's always good to check that your charges were consistent with your conditions. Good. And then the water actually came in handy here as the protic solvent to do the acid-base reaction in the second step. So notice that in this case, remember that we usually alternate between acid-base and nucleophile-electrophile reactions. Even though we added a strong base here, we actually started with a nucleophile-electrophile reaction. This is where OChem is tricky. Remember, if you start with a strong acid, if the starting materials start with a strong acid, then what always happens in the first step if you've started with a strong acid?
Acid-base reaction.
Strong acids always act like acids. But unfortunately, do strong bases always act like bases?
No.
Sometimes they act like a nucleophile in the first step. That's why it's a little bit harder. It's harder to predict the first step of a reaction under basic conditions than under acidic conditions. The first step of a reaction under acidic conditions is always an acid-base reaction. But the first step of the reaction under basic conditions could either be acid-base or nucleophile-electrophile. Okay. One other thing to notice here, notice that, do you see how the last step produced hydroxide?
Yeah.
So notice that actually the hydroxide here is what we could call a base catalyst. We haven't talked about that term, but do you see why that would be a catalyst? What's the definition of a catalyst?
Catalyst will speed a reaction without being changed.
That's right. Or maybe instead we shouldn't say it's not changed at all, but it's not changed by the end of the reaction. That is, any changes that happen get reversed by the end of the reaction. Or basically, a catalyst will speed up the reaction without being used up in the reaction. Okay. A catalyst will speed. That's basically what you're trying to say. So what you were saying was basically correct. I just wanted to sharpen that definition. So a catalyst is something that speeds up the reaction without being used up. Well, the hydroxide here is not going to get used up, because every step, this reaction both used up a hydroxide but also created one. So this would actually be playing the role of the base catalyst. Okay. There's many reactions that use acid and base, use them as catalysts, although that's not how it always works. Let's see.
I have a question about the oxides. I know that it would be that oxygen on there could work as a leaving group, which is a little unusual, but it's because of the ring strain. But it does have lone pairs on it. Could it act as a, say, nucleophile? It would be a poor nucleophile since it's neutral. But could an epoxide work as the oxygens work as a nucleophile?
That's a very good question. Good. That's good that you're thinking about that. That's good that you're not just kind of just accepting the reaction, but thinking about alternatives. That's a very good mindset there. So let's try to analyze that. So why did you say the epoxide oxygen would be nucleophilic?
Lone pair of electrons.
Right. But why did you say it would be a poor nucleophile?
Because it's a neutral oxygen.
Excellent. So that was an excellent analysis. That's good that you're using the ideas we talked about. But there's one more idea that we talked about last time. Remember we talked about what happens to a neutral nucleophile after it attacks?
It becomes more positive. It loses electrons.
So a neutral oxygen will become positive, but then what? I think you haven't quite remembered something else we talked about last time. So a neutral oxygen after it attacks usually does what? Or not just a neutral oxygen, a neutral nucleophile. What happens to a neutral nucleophile after it attacks?
It would join to the electrophile.
Let's see. No, I think that was confused. So I think you might have forgotten this idea.
Okay.
After a neutral nucleophile attacks, it usually has what charge?
Positive. But
then, is it happy with that positive charge?
No.
So what would it do to get rid of the positive charge usually?
Deprotonate.
That's what I was going for there. What happens to a neutral nucleophile after it attacks? It loses a proton.
Okay.
What happens to a neutral nucleophile after it attacks? It loses a proton.
Okay.
Do you remember we saw a bunch of examples of that last time? So that's an important slogan to keep in mind. So to review, what happens to a neutral nucleophile after it attacks?
It loses a proton to lose its positive charge.
That's right. So what could the epoxide oxygen do that?
No.
Because it doesn't have a proton.
Yeah.
So that kind of is the answer to your question. So no, it would not be a very effective nucleophile because it couldn't get rid of the positive charge after it attacked.
Okay.
So so your analysis was good. It's good that you were using some of the ideas that we thought about to see that this could be a nucleophile. And then the reason you hadn't quite gotten to the answer is because there's one more idea that you had maybe had forgotten about. So so anyway, the point is that the good thing is that we're at the point now where we've covered enough ideas that we can actually explain many different things in OChem. The only hard part is remembering all the stuff we've talked about. So yeah, neutral nucleophiles. Many things. It's hard to be a neutral nucleophile if you don't have a proton. There are some exceptions. Sometimes a neutral nucleophile attacks even without any protons, but that's pretty rare, especially in the second semester. So generally speaking, it's better for a neutral nucleophile to have a proton so it can get rid of the positive charge. Okay. So would we expect the epoxide oxygen to be a nucleophile?
No.
Why not?
Because it cannot deprotonate. It seems like the same reason also that an oxygen on a carbonyl wouldn't, because it doesn't have a proton to lose to then lose its positive charge.
Excellent, excellent. That's a very good connection, and that's exactly right. So that is something we've talked about. So previously we just memorized that carbonyl oxygens are usually not nucleophilic, but now we can kind of explain why that is. It's because they don't have a proton. So that's an excellent connection. So it is a very close analogy, absolutely. Okay, so what role do we expect epoxides to play in reactions? What role do we expect epoxides to play in reactions?
Leaving group and electrophile.
Right, not nucleophile, for the reason we were just talking about. Okay? So let's see. But anyway, it's good that you were trying to analyze that point. That's an important thing to think about. Let's see. Yes. So remember that when we started this reaction, we decided that we wanted a base. I'll write something on my screen, and we weren't quite sure what base to use. Well, often the best base to use often, not always, the best base to use is the deprotonated version of the solvent. For example, if you use a water solvent, what might be a good base to use?
Use the water solvent. A good base would be sodium hydroxide.
Because that's the deprotonated version of the solvent.
Yeah.
Of course, you could also use, say, potassium hydroxide, because the metal is just a spectator. It doesn't matter.
Yeah.
In fact, oftentimes people don't even mention the metal. People might just say the best base to use is hydroxide. You
Okay.
could just say the base is hydroxide, but maybe it's a little bit more accurate to include the metal. All right? So let's say that I use ethanol as the solvent. What might be a logical base to use with that?
Just an O- with the ethane attached.
Great. An ethyl with an O-. The name for that is ethoxide. But the name is not important. What's important is the structure. Good. We can call that sodium ethoxide. Okay, great. So that was right. Your answer was correct. It's just the deprotonated version of the solvent. Now, there's exceptions to this. Sometimes we don't do this, but oftentimes it helps to do this. One reason why this is helpful is we don't need to worry about these competing with each other. So remember that in this case, kind of what we're hoping to have happen is that the hydroxide will act like a nucleophile here and attack here. But what if there's an acid-base reaction instead, and it attacks here? Well, that's not going to mess things up, because that's just going to give us another hydroxide. That's the whole reason why it helps to use a base that's similar to the solvent. It helps to use a base that's similar to the solvent, even if you want the base to act like a nucleophile, because then we don't need to worry. Maybe I should say this is the best base / nucleophile.
Okay, yeah. Because it is a base, but it would also perhaps...
We're hoping that it'll act as a nucleophile.
Yeah.
In this case. But even if it acted like a base, who cares? Because it would just give us the same thing we started with. So the thing that a chemist is always scared of is having more than one pathway in their reaction. A chemist wants to put in reactants that can only give you one product. So he doesn't want to get one product when it acts like a base and a different product when he acts like a nucleophile. Well, that's why it's good to use a base that's the deprotonated version of the solvent, because then it doesn't matter whether it acts like a base or a nucleophile. Ultimately, the product will be the same either way. If the sodium hydroxide acts like a nucleophile and attacks the epoxide, that'll give us one product. But if the sodium hydroxide deprotonates the water and turns the water into hydroxide, and then that hydroxide attacks the epoxide, it would give you the same product as the first pathway. So that's one advantage to using. Basically, the idea is it's often helpful to use a nucleophile that's similar to the solvent, or a base that's similar to the solvent. Okay.
Okay.
So let's try to predict the results of this reaction on your screen.
Okay. I'd say no reaction because the oxygen of the alcohol here would be a poor nucleophile. We need a better nucleophile for it to react with the epoxide.
Okay, excellent. So let's try to figure out a way that we could adjust the conditions here so the reaction would occur.
Okay, I think if we added the deprotonated version of that, so like that, then that could act straightway as a nucleophile. And that way we would get our reaction with our epoxide. Since that has a negative charge, looks like we'd want that to react with the Okay.
Okay, very good. Excellent. Let's zoom out so we can see the whole thing. So what role, so you added propoxide because it was similar to the propanol. What role did the propoxide play in the first step?
Nucleophile.
What other role might it possibly play?
Strong base.
Right. But there's really no point showing it doing the strong base reaction. Why is that?
Because you'd end up with more propoxide.
That's right. So we may as well just go straight to the nucleophile reaction. Excellent. So that's why that was a good base, or nucleophile to use here. So would you say this reaction was under acidic or basic conditions?
Basic.
Because we started with a strong base, even though it actually acted like a nucleophile. It's still considered basic conditions. Okay. What role did the oxygen in the epoxide play?
Acid. Or, oh, sorry, I was looking at the other the
in the first step.
It would actually act as a leaving group.
Good. And why is that reasonable?
Because of the ring strain, it allows that neutral oxygen to act outside of the normal general rules.
Okay, excellent. Good. All right, so that's a good application of what we were talking about here. Notice that alcohols are quite similar to water in reactivity. Alcohol doesn't look that similar to water, but they're quite similar because the key atom is the same in both of them, a neutral oxygen. So things that you can do with alcohols you can usually do with water because they both have that neutral oxygen. All right, I'll go back to my screen. So what would happen in this reaction?
Nothing.
This is the one we talked about earlier. How did we say we could get a reaction to occur here?
Adding hydroxide.
That would often be written like this. Is the hydroxide added at the same time as the water or in a separate step?
Same time.
Remember, so it's perfectly okay to put them in together because they're so similar to each other that even if the hydroxide attacks the water, you'll just get the same thing you started with. So this is often written like this with a comma. The water is playing the role of the solvent. Okay, now, so how did you analyze this problem? You said, well, why is there no reaction here?
The oxygen on the water is a poor nucleophile. And
good.
Yeah,
that's right. The oxygen in the water is a poor nucleophile. So you said one way to get this reaction to occur would be to make this into a better nucleophile. And how can we make things into a better nucleophile?
By adding a base.
Right. But then it was kind of counterintuitive because if you add this base, it doesn't even have to act like a base. It's hard to put it into words. But if you add this, the purpose of the base is to deprotonate the water, but this base is already deprotonated water. But anyway, even though the logic is kind of weird, it still got us to the right answer.
Sure.
We could use a base to get a better nucleophile. In fact, if you use this base, it is the better nucleophile. All right. Can you think of any other way we could have adjusted conditions here to get a reaction besides using a base? So you said we could use a base in order to get a better nucleophile. In fact, we added a base that was a better nucleophile. But can you think of any other ways that we could adjust the conditions here to get the reaction to occur besides using a base?
Besides using a base. Well, if you added an acid, you may be able to make the epoxide a better electrophile.
Excellent. Yes, that's right. Isn't that logical? The first thing we tried was making the water into a better nucleophile. Well, the alternative would be to make the electrophile into a better electrophile. So that's also logical. So let's try that. Try writing that out on your screen. Try to write down some reagents that would use that approach.
Okay. So we've got H2O and an epoxide.
So the question is, what acid should you add? And I think the one you picked was a good one, especially because remember how we talked about how it's good to use a base that's just the deprotonated form of your solvent.
Yeah.
Well, similarly, it's good to use maybe an acid that's just the protonated form of your solvent, at least in this case. Maybe actually, I don't know. That's not maybe that's not as useful a rule. But anyway, in this case, certainly H3O plus is logical. We don't need to worry about the H3O plus competing with the water because they're both so similar. They're going to give us the same. They both give us the same outcome anyway. So that certainly is the best acid to use here. Excellent. Okay, good. Now, when you write H3O plus, what's the solvent?
Water.
So you can actually erase the water on the left. We wouldn't usually write water plus epoxide because the water is implied in the H3O plus.
That makes sense.
Okay, not that you would lose credit for that probably, but this is how it's usually written. Okay, so let's try to come up with a reasonable electron pushing arrows now.
All right. Well, okay. I, I think,
So let's back up for a second. Um,
sure.
let's put back in the arrow you just had there a second ago.
Yeah, it looks like it would just create the same thing that,
So you were rejecting that. Okay, that's
yeah,
logical. Good. Let's see if there's a faster way we could get to the right outcome here, though. So let's go back and put in the mistaken arrows for a second
sure.
so that we can analyze them again. All right, now let's zoom out so we can see the whole set of reactions. What type of reaction occurred in the first step? Acid-base or nucleophile electrophile?
Oh, yeah. Acid base.
That's obvious because anytime we start with a strong acid, we're going to start with an acid-base reaction. And then what type of reaction was the second step?
Nucleophile attack.
That's right. So what type, based on the patterns that you and I have studied before, what type of reaction would we expect for the third step?
Acid base.
Which I don't think is what you were drawing here.
Right.
So that's that. So you did eventually reject this, but we want to find a quicker way not to consider it in the first place. So it's good that you saw this wouldn't work, but we can see more quickly this is probably not the best thing to do because we've seen that generally we alternate between generally after a nucleophile electrophile reaction, generally we do an acid-base reaction.
Okay.
Now
Yeah.
that's not a hard and fast rule. There are some exceptions to that, but you wouldn't want to do an exception without thinking about it. I don't think you had specifically said, gee, I think this is an exception. I think you just maybe hadn't thought about the rule here. So the general rule which applies here is since we just did a nucleophile electrophile reaction in step 2, unless there's a good reason not to, we should do an acid-base reaction in the next step. And I think that's what you were moving towards anyway. But that's the faster way to see what's going to happen. Okay, so
Yeah,
let's try to fix those arrows.
Okay. Okay.
Okay, good. So let's zoom out. All right. By the way, so what was the solvent for this reaction?
Water.
So that's why it's perfectly okay to draw a brand new water in the third step. You just drew that water because you know there's plenty of waters from the solvent. Now,
Yeah.
what role did the water play in the second step? What role did the water play in the second step?
Nucleophile.
Good. Now, it's a neutral nucleophile.
Yeah.
Are neutral oxygens good nucleophiles?
They're poor nucleophiles.
So why is it that the water can attack the epoxide now when it couldn't before?
Because the oxygen on the epoxide now has a positive charge, making it a better electrophile.
That's
better
right.
Group. Yeah.
So poor nucleophiles are not non-nucleophiles. Poor nucleophiles can act as nucleophiles, but they have to attack something positive. So a neutral oxygen can only attack something that's positive. Of course, it's not attacking the atom with the positive charge. As usual, it's attacking the atom that's attached to the atom with the positive charge. But the point is there has to be a positive charge in the molecule that's getting attacked for water or an alcohol to attack because they're neutral oxygens. So, so neutral oxygens can only attack things that are positive. So that was an important. In this reaction. Let's see.
Okay.
That was the whole reason that we used the acid in the first step, to make it a better electrophile. So to review, what role did the water play in the second step?
The water in the second step played the role of nucleophile.
And then what role did the water play in the third step?
Acid and, well, base.
That's right. Remember that you had kind of gone down the wrong path because you tried to use water as a nucleophile twice in a row. At first you were trying to use water as a nucleophile in both steps, but that's not the usual pattern in OChem.
Yeah.
Okay? Now, just to review that one more time, what role did the water play in the second step?
Nucleophile.
And it's a neutral nucleophile. What usually happens to a neutral nucleophile after it attacks?
Deprotonates.
And that, again, is kind of what you had missed the first time. You weren't deprotonating it. That's another way to see that you were kind of missing what the third step should be. What usually happens to a neutral nucleophile after it attacks? It loses a proton. That's why we need to do the acid-base reaction next. So that's actually a quite important rule. Neutral nucleophiles usually deprotonate after they attack. You don't usually just do another nucleophile electrophile reaction. Okay.
Makes sense.
Okay. Now, let's compare this to the water attacking the epoxide at the top of your screen. So at the top of the screen, you have the water and the epoxide under basic conditions. And now on the bottom of the screen, we have the water and the epoxide under acidic conditions.
Yeah.
Compare the ultimate products of both of those paths. What do you notice about the ultimate product under basic conditions or under acidic conditions? Let's focus on the main molecule.
Looks the same.
It's the same. That's right. It's the same. So the point here is that, we got the same outcome under either acidic or basic conditions. That will often be the case. Oftentimes a reaction can be helped by either acid or base, and you get the same ultimate product either way. So it's the choice of the chemist which way they're going to do it. They might use other considerations. I guess I might mention, do you notice that we used H3O plus in this reaction, but then notice at the last step also produced H3O plus. So the H3O plus was really acting like an acid catalyst in this reaction. Okay. Just like we saw the hydroxide was acting like a base catalyst in the top reaction. So in this reaction we can use either an acid or a base catalyst and we get the same main product either way. Okay. Okay, so the lesson here is that sometimes some reactions can be helped by either acid or base.
Yeah.
All right. So I'll go back to my screen. So what would happen here?
Also no reaction.
Good. As we talked about before, we already saw this. So what we did earlier is we added a base to make this work. What would be a good base to add here?
Propoxide.
Right. That would often be written like this. Well, are there any alternative approaches we could use to make this reaction with the alcohol work? So in this case, we added a base. Putting this under basic conditions gave us a better nucleophile. So this is not a good enough nucleophile to attack the epoxide, so we put it under basic conditions, which gave us a better nucleophile. What would be an alternative approach that we could use to get a reaction between epoxide and alcohol?
Adding an acid.
Now, this is a little tricky. Any ideas what acid we might use here?
Well, I would think like H2SO4 would work.
Excellent. That's exactly what I was going for. Yes. H2SO4 would be the best acid to use here. Great. Okay. Good. Now, do you remember up here, we said we could get this reaction to work with H3O plus. But do you remember, we've seen in the past that H3O plus is basically identical to H2SO4 plus water.
Yeah.
So we've kind of been using H2SO4 even in the water case. When we use H3O plus, you can kind of think of that as a shorthand for H2SO4 plus water. It doesn't have to be H2SO4, but that's oftentimes. Remember, H3O plus just means strong acid in water, and a common strong acid that would be used there would be H2SO4. So we could just as well have done the water reaction with H2SO4 plus water instead of saying H3O plus. You see it often either way in organic chemistry classes, although this is a little bit simpler to write down. Okay, so let's try diagramming out this reaction.
Okay.
With the arrows on your screen. Let's be a little careful with the first step and make sure we show the two charges that are changing. Okay, good.
Okay, kind of a long reaction.
Okay, good. How many steps were there?
3?
Really only 3 steps, but it was a long molecule, so it took up a lot of space. Okay, so good. How did adding the acid help the reaction?
It made the epoxide a better electrophile.
That's right, so that the neutral oxygen could attack it. Neutral oxygens need a positive charge before they can attack. Good. Why didn't we, so what role did the oxygen play, what role did the alcohol play in the second step? What role did the alcohol play in the second step?
Nucleophile.
Why didn't we use the hydrogen sulfate as the nucleophile, since that has a negative charge?
Because it is resonance stabilized.
So it's really unreactive. Good,
Yeah.
as we've talked about in the past. Good. Okay, so notice we've just done a bunch of epoxide reactions in a row. We were trying to kind of learn some patterns that often occur with epoxides and how we can help the reactions in this case by using either acid or base. Good. And one thing we're starting to do is we're not just seeing when we can use acid or base, but we're starting to try to get some feel for what acid or what base is appropriate in different conditions. Okay, I'll go back to my screen.
Okay.
So what role do these play in reactions?
Base.
Okay, done. You're saying they're playing the role of a base?
Yeah.
Okay. All right. Actually, that's misremembering. I think you might just got confused here because usually when we get this right.
So I guess they would actually be a nucleophile because they're such a strong acid that the conjugate base would be irrelevant in this case.
That's right. So even though they have negative charges, they're not really very basic. On the other hand, we use them as nucleophiles all the time. These are some of the most common nucleophiles, so I guess we got a little bit confused about that. All right, so in fact, these generally play the roles of nucleophiles. We see them do kind of simple SN2 reactions all the time, like this. Okay? All right, So that's where review comes in. That's very important. Again, a chess player has to always know how the bishop moves, not just 98% of the time. So we have to be confident that we can always retrieve the information that we need for these, and that just takes continual review. All right. What role does the carbonyl oxygen play in reactions?
Base.
Strong or weak?
Weak.
Good. Is the carbonyl oxygen usually nucleophilic?
No.
Why not?
It could not lose a proton to lose its positive charge.
After it attacked. Good. Yes,
Yeah.
because it doesn't have a proton. That's a good point. Good. What role does this play in reactions?
Base. Strong base.
Is it a nucleophile?
Nope.
Yeah. How do you know? Well, we just memorized that. We didn't really explain it. What role does this play in reactions?
In the presence of an acid, it would act as a base, strong base. And without an acid, it would act as a nucleophile.
Excellent. What role do we probably want it to play?
Nucleophile.
Okay. That's kind of a long thing to write out, but what you said there was correct. Good. So it is a strong base. Good. What role does this play in reactions?
The same. It is, yeah, it is strong base in the presence of an acid, but preferably a nucleophile.
What role does this play in reactions?
Also the same.
What's the name of this type of compound?
Grignard reagent.
And this?
Alkyl lithium.
And this?
Lithium aluminum hydride.
That's a logical name. I find that people often confuse these two because they both have lithium, so we have to be careful not to confuse them, even though they both have lithium. What role would this play?
That would play the role of a nucleophile, not as a base.
Technically, it is a weak base.
Okay.
So I'll write that down. Pretty much anything that's nucleophilic is at least a weak base, but you're almost never going to see it play that role. It's not a strong base like these are. So it's almost always going to play the role of a nucleophile. I'll just say technically it's also a weak base, but I'll put that in parentheses because we're not really going to see it do that. Okay. What role can this play in reactions?
That could be a weak base, a poor nucleophile, or an acid.
Strong or weak acid?
Weak acid.
So obviously, what's the name of this molecule?
Water?
It plays a very important, and oftentimes, of course, it's often just the solvent, but these are the active roles that it can play. So that's a good discussion of all these various roles that water can play. Good. It's a poor nucleophile. That means it can't attack something unless it has a positive charge.
Yeah.
What role would this play?
Strong acid.
Anything else?
No.
That's pretty much it, yeah. This is a strong acid. Good. What role would this play?
A strong base or a nucleophile.
Okay, good. It's tricky. It can be hard to tell which one it's going to be. O minus is tricky. Sometimes it's hard to tell whether it will be a strong base or a nucleophile. All right, do you see why I talked about these three together? H3O plus is just protonated water, and sodium hydroxide is just deprotonated water. So these are all closely related to each other. But you can see adding or removing a proton has a huge effect on the reactivity. Why? Yeah. Why does adding or removing a proton have a huge effect on the reactivity?
It affects the charge.
That's right. And what's the most important factor in organic chemistry? The charges. Why are acid-base reactions so important? Why do acid-base reactions affect reactivity?
They always affect the charge.
Yeah, maybe that was a weird question, but that was the answer I was going for. Yes. Remember, an acid-base reaction is just transferring a proton. Acid-base reaction is just moving a proton from one place to another. But the key thing is protons are charged. So anytime you move a proton from one place to another, it might not seem like a big deal, but you've changed the distribution of charges. So this is the reason why acid-base reactions are so important, because they change the distribution of charges. So these are very important in chemistry. Acid-base reactions are important in chemistry because they change the distribution of charges. Acid-base reactions are also very important in biochemistry. So the processes in our body, oftentimes the body will just add or remove a proton from a substance to change its reactivity or its behavior. Okay. So I'm sure you've noticed that in chemistry and OChem, people talk about acids and bases a lot. But why? Why do we keep talking about acids and bases? Why are they interesting? It's all because when you move a proton, you change the charges. Oftentimes, I think that's not really clear to people. The reason why we're interested in moving protons around is because it changes the pattern of charges. Okay?
Okay.
What type of functional group is this?
Alcohol.
Right. So what role would we expect this to play in a reaction?
Virtually the same as water, a weak base, weak acid, or poor nucleophile.
Good. What role would we expect this to play in a reaction?
A strong acid.
Anything else?
No.
This is a little tricky. I suppose if this, we know that if you start with a strong acid in the very first step of the reaction, it'll act like an acid. But if you generate strong acids during the reaction, they don't always act like acids. They can play a different role. What other role could this play besides strong acid?
Not quite sure.
Well, let's focus on the charge. What role could the charge allow it to play?
Well, things with positive charges are acids, electrophiles, leaving groups. But I don't think it could be a leaving group. I don't think it could be an electrophile.
And why not?
Because it already has, it doesn't, because only electrophiles that have positive charges are carbocations.
Okay, so first of all, let's not just focus on the one individual atom here. What role could this molecule play? Maybe we're getting a little confused.
Well, I think
you had said earlier that, I'm sorry, go ahead.
Sorry, it could be an electrophile. It could be an electrophile because I was thinking it couldn't because it would, if that were a leaving group, you would cause there to be a primary carbocation. But if it is if carbon, say 3, which is attached to the oxygen, if that were to be an electrophile, it would not become a carbocation because it would join a nucleophile, and there the oxygen could be a leaving group. So as a molecule, that could be an electrophile with a leaving group.
Okay, yeah, that's right. So the point is, maybe you were thinking of the leaving group leaving just on its own. But remember, oftentimes the leaving group leaves at the same time that the nucleophile attacks.
Yeah.
So what's the other role this molecule could play besides strong acid?
Electrophile and leaving group.
Right. We would say the molecule is the electrophile, although that's because it has a leaving group. After all, I think we've seen reactions like this quite frequently.
Yeah.
Okay. So maybe you were a little confused on that one. How can you tell which it's going to be? How can you tell whether it'll act like an acid or like an electrophile? Well, it's by using the pattern we've talked about. If you just did an acid-base reaction, you should probably follow that up with a nucleophile-electrophile reaction. On the other hand, if you just did a nucleophile-electrophile reaction, you should probably follow that up with an acid-base reaction. So in this case, it wouldn't be too hard to figure out which role it was going to play, because you could look at the previous step. We wouldn't usually have this as one of the original starting materials. This would probably be generated in the course of the reaction. Okay, but you know, now that I'm thinking about it, all of these reagents I've used so far, I've been kind of focusing on how they would react if they were present in the first step of the reaction. So maybe it was unnecessarily confusing to bring this up, because this would generally be generated during the reaction. It wouldn't be added in the first step. So maybe I'll take a step back and erase that one. Maybe that was more confusing than it was worth. And we'll keep talking about what roles things can play if they're added in the first step. Maybe that'll be more helpful for us. So I'll erase that. And we'll go back to here, and then we could ask, what role would we expect this to play in a reaction?
A strong base or a nucleophile.
And it could be difficult to tell which one. You'd have to look in more details to try to figure out which one it would be. Okay? What role would we expect this to play in a reaction?
Nucleophile.
Any other possible roles?
No, I think that is all it would play.
Let's see. So there is another role that this could likely play. Could it be an acid or a base?
It could be an acid. A weak acid.
All right. Now, actually, we've seen that an N with an H is a very weak acid, too weak to really be worth worrying about. Maybe this is a little hard to remember at this point. But remember, the nitrogen is not really electronegative enough to really want to donate a proton. It's not electronegative enough to really want a negative charge. Any other roles besides acid and nucleophile?
Base, with its lone pair of electrons.
That's really what I was going for, yeah. Strong base or weak base?
A weak base.
Because it's not in the list we've memorized of strong bases. Okay, so this would probably usually be a nucleophile, but I think it's important to know that nitrogens are common weak bases as well.
Okay.
So what role would you expect this to play?
Either a nucleophile or a weak base.
Right. How could you tell which one it would be? Well, remember, it's probably not going to play the role of a base unless there's a pretty strong acid around. Okay. What role could we expect this to play?
That could be a nucleophile or a weak base.
Good. Because we've learned that carbon-carbon pi bonds can play those roles.
Yeah.
Good. What roles could we expect this molecule to play?
Electrophile.
Which atom is electrophilic?
The carbon of the carbonyl.
Carbonyl carbon is electrophilic. Good. What makes it electrophilic?
The delta positive.
Excellent. Good. Any other roles this molecule might play?
Seems like it does not play the role of a nucleophile because it could not lose a proton to lose its positive charge.
Good point.
But I think it could play the role of a base because of the lone pair. A weak base. The oxygen could.
That's right. So which one will it be? Which one will it act like an electrophile or like a weak base? Well, if there's a strong acid around, then we'll do the acid-base reaction. And if there's no strong acid, we'll probably start with a nucleophile-electrophile reaction. Okay, good. Later in the second semester, you'll learn another role that this can play. Or maybe we'll get to that later, but we're not quite ready for that yet. Okay, so what role might we expect this molecule to play?
Electrophile or a weak base.
Which atom is the electrophile?
The carbon. Either carbon.
Carbon is electrophilic. Good.
The oxygen would be a leaving group.
Because of the ring strain. Good.
Yeah.
And you said weak base?
Yeah, the oxygen could be a weak base with the lone pair of electrons.
How do you know which one to start with then? Well, if you've added a strong acid, then you'll get the acid-base reaction. Otherwise, you'll probably get the nucleophile-electrophile reaction. Okay, good. What roles might we expect here?
You could have a weak base.
Because of the lone pair on the oxygen. Good. Anything else?
No, I think that's it.
Let's see. Why couldn't this be a nucleophile?
It wouldn't be able to lose a proton to lose its positive charge.
Excellent. That's good that you used that idea. We hadn't applied that to this before, so that's an excellent point. That's the reason why none of these oxygens are nucleophilic. None of these oxygens are nucleophilic because none of them have a proton to lose. Good. By the way, if you remember, this is what's called an ether.
Okay.
So anyway, the point here is that ethers are usually not particularly good, are usually not really nucleophilic because they don't have that proton. So usually you'd have to start with an acid-base reaction to get anything happening here.
Okay.
Do you remember how we said that water is pretty similar to alcohol?
Yeah.
Ethers look kind of similar to water and alcohol, but an important difference is they don't have a proton to lose. So they generally can't act like nucleophiles, whereas notice, say in alcohol, because of the proton, it has more different roles it can play. Okay, good.
Okay.
So what role would we expect this to play in a reaction?
Nucleophile. The chlorine.
Could it be a base?
No.
Usually not, because it's the conjugate of a very strong acid. Good.
Yeah.
what role would we expect this molecule to play?
Electrophile.
The carbon is the electrophile, and what role would the chlorine play?
Leaving group.
So notice there's a huge difference between this chlorine and this one, because their charges are different. And what role would we expect this molecule to play?
Strong acid.
Great. What role do we expect this to play?
Strong acid.
Great. What role do we expect this to play?
Spectator.
Excellent, because of the resonance stabilization. What role might we expect this to play?
I don't know. It seems like that has resonance also. It does have the pi bonds, which are typically nucleophilic or weak base. So I guess if you had a really good electrophile or a really strong acid, you could maybe get a reaction there.
Okay, that's actually a very good analysis. That's good that you noticed the resonance. That's good that you thought about the resonance. So that's right. It is. This is resonance stabilized. Does that make it a better nucleophile or a worse nucleophile?
Worse.
Worse. Because does the resonance make this more stable or less stable?
More stable.
Does that make it more or less reactive?
Less reactive.
Yeah. Okay. So that was a very good analysis. It's good that you applied resonance to thinking about that. We haven't talked about that much, but that was good. Nevertheless, this could be a nucleophile. Theoretically, it could be an acid, but I can't think of any interesting reactions where that would happen. So maybe I'll say it could technically be an acid, but I'm not going to write that down because I can't think of any interesting reactions in the introductory course where it acts like an acid. So I won't write that down, even though I can see why you would have predicted that. But there are some important reactions in the second semester where it's a nucleophile. Basically, what is the second semester about? The second semester is about carbonyls. And do you know what the name of this compound is?
Benzene?
Yeah. Those are the two main topics in the second semester. The two main topics in the second semester are carbonyls and benzene. You and I have spent more time so far talking about carbonyls, but benzene is also another important topic in the second semester. But you already gave a pretty good analysis of how you might expect the benzene to react. So that was a good way to think about that. Okay.
So would that almost fall in the category of a poor nucleophile, like an oxygen? I'm not sure.
Let's see. Yes. You know, that's true. It really is, because the key thing about neutral oxygens is they can't attack something unless it's positive. Yeah. And that actually is true of benzene. Benzene will not act as a nucleophile unless the thing it's attacking is positive. Okay. So that is a good point. I hadn't thought about that. But actually that is a fair point. In a way, it belongs in the same category as the neutral oxygens. What is it that's making this a poor nucleophile?
Resonance.
The resonance, yes. So you can start to see how resonance can help us to alter our predictions here. How about this? What role do we expect this to play in a reaction?
NH3 nucleophile.
Good.
Or,
is it a poor nucleophile?
I don't think so.
No, because we just said earlier that neutral oxygen was pretty much the only poor nucleophile, although we just expanded it to benzene. But you should generally assume, so notice, can something that's neutral be a good nucleophile?
Yeah.
So could this attack something that's neutral? Can ammonia attack a neutral electrophile?
Yeah.
Yes. Can alcohol attack a neutral electrophile?
No.
Because it's a poor nucleophile.
Yeah.
Good. Can benzene attack a neutral nucleophile, a neutral electrophile?
No.
No, because it's a poor nucleophile. So we've only talked about now two types of things that are poor nucleophiles that are neutral: benzene and neutral oxygens, basically water and alcohol. Other neutral molecules like NH3, those are still pretty good nucleophiles, even though they're neutral. Good.
Okay.
Okay, so this is obviously I'll send you my tutoring notes as usual. Hopefully you were taking notes on this anyway. But I think this is a real important summary table of the kind of the characters in organic chemistry. This covers a really broad range of the most important types of molecules that you're likely to see in organic chemistry. A lot of these ideas, we've learned rules to figure them out, but also some of these ideas just have to be memorized. So this table is a combination of applying our rules and also just some regular memorization. But it's important to be very comfortable with all of these. If you're comfortable with these, it makes it much easier to figure out what's going to happen in a reaction if you don't remember, and it also makes it much easier to just to memorize the reactions. Sometimes, even if you're just memorizing a reaction, it's easier to memorize it if you see how it falls into the patterns we've talked about so far. So,
Yeah.
on the one hand, this is kind of discouraging because look how many characters there are here. But on the other hand, actually, it should be encouraging because you already know almost all of these. Almost all of these you got right. There was a couple places where I had to give you some help, but the great bulk of these you already figured out on your own. So this is kind of a good mark of how much progress we've made. The great bulk of these you actually were able to figure out on your own without any help from me. And this covers the large majority of what you're going to see in OChem, even in the second semester. Obviously, there's some stuff that's not in this table yet. This covers a pretty big fraction of the reagents in OChem right here. So if you can really memorize this pattern, that gives us a big head start. And I think we already have a lot of it already memorized. Okay, good. So to continue. Okay, so I'd like you to predict the product of this reaction on your screen.
All right. Okay.
Okay. What was your thinking?
Well, with the carbonyl here, the oxygen could act as a weak base, but there is not a strong acid for it to react with.
Good.
The carbon could act as an electrophile, but the only nucleophile present is a poor nucleophile that would need a positive charge to attack.
Okay, good. Excellent. So no reaction. All right, so can you think of any way we could adjust conditions to get a reaction here?
Yeah, if you added either an acid or a base, you could actually get a reaction out of it. It'd have to be strong, but I think we typically like to add something as close to the original solvent as possible.
Oftentimes, yes. Good.
Yeah. So if we did add a strong acid, like a hydrosulfuric acid with water, then we'd actually have... Should I go ahead and write it out?
Let's go ahead and do it, sure.
Okay. Then we would have acid-base reaction. because water is the solvent, I can pull another one
Great.
out of there. And the H3O plus would basically be a acid catalyst, ending up with the same at the end.
That's right. That's a good analysis. It did turn out to be a catalyst. Very good. Okay. Excellent. All right. Very good. Remember that carbonyls are one of the two most important functional groups in the second semester. So this is a second semester reaction that you'll see in the second semester. Now we've already seen it. Okay, good. Can you think of any other ways to make this reaction, to adjust the conditions to get a reaction to happen here?
Sure, if we added something like hydroxide, I think we'd write that out as well.
That would be the solvent. Good.
Yeah, in a solvent of water. So, that would
Okay,
act
so what role is the hydroxide playing?
as a nucleophile.
Right. Are these acidic or basic conditions?
Basic.
But there's no point using it as a base because you just get another hydroxide. Okay, good. Now this is a real reaction that you just wrote out. This is a real reaction. It's in the introductory textbook. However, this particular reaction usually is not tested in the introductory course, so we won't continue with it. I think you can probably figure out the rest of it.
Okay.
But this particular reaction is usually only tested in the acidic conditions, even though it could occur either way. Even though they're both in the textbook, usually only the acidic condition is really focused on in the course. So we won't continue with this approach. In fact, we can erase this right now. But it certainly is a real reaction. So not all real reactions are really focused on too much in the introductory course. So both reactions are real, but it's the acidic conditions that you probably focus on in your course. But the basic reaction would make good sense too. Good. So I'll go back to my screen. Excellent. So let's predict what would happen here.
Again, there would be no reaction because there really is not a good nucleophile to attack that carbonyl electrophile.
Good.
And there's not a strong acid to react with the weak base oxygen carbonyl.
That's a good analysis. That's a good analysis. Great. So let's try to adjust the conditions so we can get a reaction.
Okay. First, let's try adding an acid.
Excellent. So that's a good acid to add.
Okay. Oh wait, no, that's not what we want to do. We want this carbonyl to be the base. Okay.
Okay, excellent. So does it look like we're done?
Yeah.
Because it looks like the main molecule has no charge. Now, actually, so this is an important reaction from the second semester. Actually, this reaction does continue. There are more things that happen. We go through another round of nucleophile-electrophile reactions. There actually is another round of a nucleophile-electrophile reactions that actually happens here when you study this in the second semester. But that actually breaks out of the pattern we've been talking about. We've just been focusing on reactions that just do one nucleophile-electrophile reaction. So I don't think we'll take this any further. So later on in the second semester, or maybe together, we'll look at those more further complications. We won't take it any further right now. So this reaction really does continue, but this is as far as we're going to take it, because this is as far as we can get based on what we've learned so far. If there's going to be a second round of nucleophile-electrophile reactions, that kind of is a slightly different pattern than we've talked about. So anyway, this is a good start. It was a good acid you brought up using the H2SO4. That's very good. I'm going to go back to my screen for a second. I did want to point out something I should have mentioned before. There's another way that this is commonly written. Oh, well, first of all, I noticed that at first you tried protonating the alcohol, but then you caught yourself. How do you know not to protonate the alcohol? Well, first of all, if you protonate the alcohol, there aren't really any other interesting reactions that you can have happen, because this is not going to be nucleophilic. So there's not much point protonating this alcohol to make it electrophile, because this is still not nucleophilic.
Yeah.
Or you can just memorize. If you have a strong acid around a carbonyl, what's going to happen?
If you have a strong acid around a carbonyl, the oxygen will act as a base.
The carbonyl oxygen.
Yes.
So the point is, you can just memorize. Anytime there's a carbonyl around a strong acid, it's the carbonyl oxygen that's going to be protonated, not any of the other oxygens.
Okay.
I did want to point out, and you caught yourself and fixed that, so that was good. Here's another way this is often written. You might have seen this in the past. Oftentimes, chemists are lazy and they don't write out the whole acid. Oftentimes, the chemists are lazy and they just write H+ to mean a strong acid. I think for a beginner, it's probably better to write the actual acid, but it's important to be familiar with this because it's actually a very common way that these are written in the textbook. So you can basically think H+, you can kind of, when you see H+, you should probably think that means H2SO4. H+ just stands for a strong acid. So if you see H+, you would do basically the same type of reaction. In fact, maybe we should start practicing that a little bit because it does come up sometimes. Let's try drawing the electron-pushing arrows if they just wrote H+. We should probably have practiced that. So on your screen, try to draw what the electron-pushing arrows would be if they just wrote H+ instead of H2SO4.
Okay.
Okay, well, I think we can stop here because the rest will just be the same as before. So let's scroll up so we can compare this to what we have previously. Notice that the second step you're drawing is the same as the second step you had up above. Okay, so I just wanted to point out it doesn't really change much whether you show it as H2SO4 or as H+. Okay. The only difference is now we're not showing the hydrogen sulfate. But you can see why chemists don't bother drawing the hydrogen sulfate because it's just a spectator anyway. So yeah. I think for a beginner it's better to write it the way we wrote it up above. But you need to be familiar with this shortcut because it's used so often by instructors and in the textbook. Okay, good. So I'll go back to my screen. We could have added that to our list then. So if you see this reagent, what role is it going to play in the reaction?
Strong acid.
Yeah, it's just a strong acid.
So that's almost a shorthand for H3O+?
Now, I wouldn't quite say that because H3O+ means something a little bit more. So it doesn't just mean you have a strong acid. What's the solvent here?
H2O.
Water. But here the solvent doesn't necessarily have to be water, although it could be. Okay. So this means strong acid with a water solvent. This means strong acid, and they're not telling you the solvent.
Okay.
Okay. Although oftentimes it's assumed water is the solvent. It might be assumed water is the solvent, but this does not kind of guarantee that water is the solvent like it would here. So what you said was close to being true. These are very similar. Sometimes they're used interchangeably, but they're not quite interchangeable because this means strong acid in water, and this means strong acid, but the solvent is not guaranteed to be water, although maybe that's often assumed. Okay. So oftentimes people will then write this. Sometimes they'll do this, and this really does mean the same exact thing as H3O+.
Okay.
Sometimes they'll write H+ and water, and that really is the same thing as H3O+. Then you know for sure that water is the solvent. All right, can you see anything else you could do to get this reaction to occur besides putting this in acidic conditions? This reaction.
Sure, if you added a strong base, you could make the ethanol a better nucleophile.
What base might you use?
Hydroxide?
Like
or
so?
Actually, the ethopoxide? I don't know how what it's called.
Ethoxide.
Ethoxide, okay.
Like so?
Yeah.
And then what role would you expect the ethoxide to play in the first step?
Just a nucleophile.
That's right. There's no point using it as a base because then you would just get the same thing you started with. Okay, so this is very reasonable. This is better than hydroxide because now we're using a base that's more similar to the solvent here, to what we want to be the nucleophile. All right, I'm not going to continue with this because, again, even though this is a real reaction, it's usually not focused on in the course. So this is a real reaction, but it's usually not one the course focuses on. Okay, so we'll just write through it. We just wrote out the acidic reaction here. Good.
Okay.
Okay, let's try to write out this reaction.
Okay.
Okay, so let's discuss this for a second. What type of reaction did you do in the first step? Nucleophile, electrophile, or acid-base?
The first reaction... Yeah, good point. I did a nucleophile, electrophile reaction.
Okay, and then you said good point. What do you think the point is?
That we should be looking for an acid-base reaction next.
That's right. So what you wrote actually is somewhat reasonable. What you wrote is somewhat reasonable, except that maybe all the carbonyls are already gone because the sodium borohydrides got to them first. In any case, this is probably not what we're going for in our course. Usually we don't do two nucleophile electrophile reactions in a row unless we've specifically learned it that way. So like I said, there are some exceptions. Sometimes you do two nucleophile electrophile reactions in a row, but usually only when you've learned that it happens that way. Now, why did you think you, so let's erase those steps. Those steps are reasonable, but they're probably not what we're usually going for in the course.
Okay.
Because they don't follow our normal pattern. Now, you weren't happy with this because it was charged. Now, what usually happens after the nucleophile-electrophile reaction? What usually happens next?
Usually an acid-base reaction.
So why didn't you do an acid-base reaction? Maybe because you couldn't see anybody here to act like the acid. Well, what that means here, remember that what we're trying to do now is not just predict what's going to happen, but if we have, sometimes the reagents haven't been written out well to accomplish what the chemist might want. So basically, this is again maybe a poorly designed reaction, because even though the first step happened, then there was no one around for the protonation step. This chemist didn't plan ahead to figure out what would happen in the protonation step. So remember that now we're trying to work on adding extra reagents that will help the reaction to work better. So what might we add now that would help us to, we need to add someone who can do the protonation step, basically.
Strong acid.
Let's see. Now, are you going to add that in a second numbered step or in the same step as the first step?
You can add it in the same first step.
Now, if we added a strong acid, that wouldn't work, because remember, sodium borohydride is a weak base.
Oh, okay.
So basically, what we should do now is we just want to add a protic solvent. Usually, the protonation step is just taken care of by the solvent. And this chemist just messed up because they didn't say what the solvent was. So let's just add a solvent. What might be a protic solvent we could use?
Water.
Yeah, water would be fine. For some reason, this sodium borohydride is usually written as used with an alcohol. I think water would probably work, but let's write it with an alcohol instead, because that's more conventional. Usually it's used with methanol or ethanol. So let's write one of those.
Okay.
Although I think water would be fine too, but it's usually written with methanol or ethanol. So again, as in the previous cases, we hadn't written out all the best reagents. So if this was really done with a non-protic solvent, we would be stuck with that negative charge. But that's probably not what the chemist intended. So we should add in this extra solvent here. And now let's continue. Then, what would be the next step?
And we'd have an acid-base reaction.
Good. Okay, are we done?
Yeah.
Yeah, now we're done. So is the methanol going to be added at the same time as the sodium borohydride or in a separate step?
That could be in the same step because it is not a strong acid.
And the sodium borohydride is not a strong base. Good. Okay, so the way you've written that is fine. Okay, so I'll go back to my screen. This is a reaction that's usually important in both the first and the second semester. You might have already seen this in the first semester, but it's also important in the second semester. I'll go back to my screen. So let's try to draw out the reaction here.
Okay. Okay, looks like we'd have to add an acid, a protic, a second step, so that that oxygen could lose its negative charge. It would have to be a separate step because the lithium aluminum hydride would act as a strong base in the presence of any acid.
That sounds like a good analysis. So again, it looks like the chemist here didn't really write out the full reagents they would need. If they really only did this, they would end up with a negative charge on the oxygen, which is probably not what they intended. So let's fix the reagents so we can get more what the chemist probably wanted to have happen here.
Okay. I guess in this case it would not really matter if we used a strong acid or a weak acid.
That's right. But as we've discussed in the past, since the whole purpose is protonation, we might as well go for overkill and use the strong acid.
Okay, yeah.
But you're right. Theoretically, even a weak acid would probably do the trick here.
Okay.
So some textbooks actually write the second step as water, but most textbooks write it as H3O+. Okay, good. Okay. All right, so conventionally, lithium aluminum, theoretically, we could use any strong acid in the second step, but what's most commonly used is H3O+. Why couldn't we just add H3O+ in the first step?
Because the lithium aluminum hydride would act as a base before it acted as a preferred nucleophile.
Right. Well, why not just use water in the first step then? Because water is only a weak acid.
Still, it's a strong base.
So even the water would destroy the lithium aluminum hydride. Yes.
Right.
So if you scroll up, notice we want to compare lithium aluminum hydride and sodium borohydride. How are they similar? Well, they're both intended to be used as nucleophiles. But how are they different? Lithium aluminum hydride, well, how are they different?
Well, you have to do separate steps with the lithium aluminum hydride, whereas you could mix the sodium borohydride in a protic solvent.
That's right. Theoretically, we could use water with the sodium borohydride, but for some reason, the textbooks usually use alcohol. Okay, good. All right, so we're about out of time, but anyway, I'll go back to my screen. So now what we're starting to do is, again, we're starting to come up with the reagents ourselves, or at least to come up with the acids and bases that we need for these reagents ourselves. And that's an important skill that helps you to remember the reactions, and it also helps you to come up with the reagents yourself when you need to fill in the blanks or do a synthesis. I think we've been making some good progress on that. Okay, so I'm hoping maybe to spend one more session or part of a session on this, and then go on to the next topic, which would be resonance. You've already started thinking about resonance, so I think we're starting to get towards the end of this topic. We've covered most of the stuff we need to cover for this, so we probably can finish this in one more session or part of one more session, and then move on to resonance, which is another important topic for both semesters. But I think we made some good progress so far. So as usual, obviously, you should carefully review what we've been talking about. I think we have made some good progress. Every once in a while, though, I'll notice that you get a little bit confused about the ideas. That's natural because we've gone over so many ideas. But remember, you just want to keep reviewing so that those moments of confusion happen as seldom as possible. This little table here is especially useful to review and to try to come up with on your own. This really covers the majority of the reagents in both semesters of OChem, this table here. And it seems like a lot, but we actually already have a lot of it memorized. So actually the most important thing is to make sure you don't start forgetting this. I think you already pretty much know this table, but it would be easy in a couple weeks to start forgetting it. So this is an important table to make sure you don't lose in your notes. One problem with getting a lot of tutoring is that oftentimes people start having pages and pages and pages of notes, and the important notes get lost. So this table is something you want to make sure doesn't get lost in your notes. It's something you want to keep reviewing throughout the tutoring, and this would be a good thing to keep reviewing during your OChem course as well, because this really covers a lot of the stuff that comes up in the course. We talked about one case where learned something about epoxides today. Epoxides have an acceptable leaving group because of their ring strain. We reviewed how neutral oxygens are not. Neutral oxygens are poor nucleophiles. That was important as well.
Thanks for your help. I do feel like we are making a lot of good progress. The ideas, the principles in the organic chemistry are a lot more concrete in my mind than they ever have been. So it's very helpful.
Okay, good. I hope so. So I hope that I think we've made some good progress, and I hope that will be helpful to you. You can see why students oftentimes don't get that feel for the topics in the course, though, because the instructor, to be fair to them, doesn't really have the time to kind of go over it. So usually what happens is the instructor just kind of dives into all the specific reactions, and because the student doesn't know these general principles, they end up just having to memorize every single detail of every single reaction, which puts an impossible strain on their memory, and it means that they can't adapt to anything. If the problem is even slightly different from what they've seen before, they don't know how to do it because they don't know what these principles are, and they don't know what the principles are because the instructor hasn't covered the principles, and the instructor hasn't covered the principles because there isn't enough time in the course to do that. But since, so I think this is effective here that we have this a little extra time to go over the general ideas. So then when you start looking at the specific reactions, they'll be much easier to remember, and it'll be easier to figure stuff out if you haven't seen it before.